Addressing single-phasing issues requires careful consideration of several factors. Firstly, regarding the time delay, a 3 to 5 second delay is generally reasonable for avoiding nuisance trips caused by momentary voltage sags. However, it's crucial to consider the startup currents of the motors and air conditioning units. A time delay that is too short might lead to tripping during normal operation, while a delay that is too long could undermine the effectiveness of protection against sustained phase loss. Secondly, the trip power source needs careful attention. It's essential that the phase loss sensor has an independent power source that is not compromised by the phase loss itself. One solution is a secondary power source, such as a battery backup, or tapping a separate phase from the distribution line. If the phase loss occurs in the same leg powering the shunt trip, insufficient voltage could prevent the main from tripping. Always verify the wiring diagram and explore alternative trip power options as needed. Other important considerations include coordination. Ensure the phase loss protection is coordinated with the main breaker. This prevents cascading trips and potential equipment damage. Regular testing is also essential. Routinely test the phase loss protection system to confirm it's operating correctly. A maintenance plan is important to ensure the phase loss sensor and its components are well maintained. Finally, consider alternatives to pneumatic relays for the time delay. A solid-state relay with a built-in time delay function can be a more reliable option, being less susceptible to environmental factors. When dealing with motor protection and phase loss scenarios, several factors should be carefully evaluated to ensure effective and reliable operation of electrical systems. This includes understanding the specific motor characteristics, load profiles, and potential causes of single phasing to implement the most appropriate protection strategies. Firstly, it is important to analyze the motor characteristics, including horsepower, voltage, full load amps, service factor, and thermal overload protection. These parameters help determine the motor's susceptibility to damage from single phasing and inform the selection of appropriate protection devices. Secondly, consider the load profiles, which involve understanding the typical operating conditions and load variations experienced by the motors. This includes assessing the frequency and duration of starting cycles, load surges, and periods of light or no load operation. Analyzing load profiles helps identify potential stress points and optimize protection settings. Thirdly, investigate the potential causes of single phasing. Single phasing can result from various factors, including utility supply issues, damaged wiring, blown fuses, or malfunctioning circuit breakers. Identifying the root causes of single phasing helps implement targeted preventive measures and protection strategies. A phase loss relay is a crucial component in protecting three-phase motors from the harmful effects of single phasing. These relays continuously monitor the voltage or current in each phase of the three-phase power supply and detect any imbalances or loss of phase. When a phase loss condition is detected, the relay quickly trips the motor's circuit breaker or starter, preventing the motor from operating under single-phase conditions. Phase loss relays come in various types, including voltage sensing relays and current sensing relays. Voltage sensing relays monitor the voltage in each phase and trip when the voltage drops below a preset threshold. Current sensing relays, on the other hand, monitor the current in each phase and trip when the current becomes unbalanced or exceeds a certain limit. Overload relays are essential for protecting motors from thermal overload conditions. These relays monitor the motor's current and trip when the current exceeds the motor's rated full load amps for a prolonged period. Overload relays are typically thermal or electronic and are designed to protect the motor from overheating and insulation damage. Fuses and circuit breakers provide overcurrent protection for motors. Fuses are single-use devices that melt and interrupt the circuit when the current exceeds their rating. Circuit breakers are reusable devices that trip and interrupt the circuit when the current exceeds their rating. Selecting the appropriate fuse or circuit breaker rating is crucial to protect the motor from overcurrent conditions without causing nuisance tripping. Motor starters are used to safely start and stop motors. They consist of a contactor, overload relay, and sometimes additional control components. Motor starters provide a convenient and reliable means of controlling motors and protecting them from overloads and short circuits. Variable frequency drives, also known as VFD, offer advanced motor control and protection capabilities. VFD can precisely control the motor's speed and torque, optimizing its performance and energy efficiency. They also provide built-in protection features such as overcurrent, overvoltage, undervoltage, and phase loss protection. Soft starters reduce the inrush current during motor starting, minimizing voltage dips and mechanical stress in the motor and connected equipment. Soft starters gradually increase the voltage applied to the motor, allowing it to start smoothly and without excessive current draw. Surge protection devices, known as SPD, protect motors from voltage surges caused by lightning strikes, switching operations, or other electrical disturbances. SPD divert the surge current away from the motor, preventing damage to its insulation and electronic components. Insulation monitoring devices continuously monitor the insulation resistance of the motor windings. These devices detect any degradation in the insulation and provide an early warning of potential insulation failures. This allows for proactive maintenance and prevents unexpected motor breakdowns. Ground fault protection is essential for protecting motors from ground faults, which occur when current leaks from the motor windings to ground. Ground fault protection devices detect these leakage currents and quickly trip the circuit breaker, preventing electrical shock hazards and minimizing equipment damage. Harmonic filters are used to mitigate the effects of harmonic distortion in electrical systems. Harmonic distortion can cause overheating, voltage distortion, and equipment malfunction. Harmonic filters reduce the amplitude of harmonic currents, improving the overall power quality and protecting motors and other sensitive equipment. Power quality analyzers are used to monitor and analyze various electrical parameters, such as voltage, current, power factor, harmonics, and transient events. These analyzers provide valuable insights into the health and performance of electrical systems, helping to identify potential problems and optimize motor protection strategies. Implementing a comprehensive motor protection strategy involves combining various protection devices and techniques to address different types of electrical faults and abnormal operating conditions. This may include using phase loss relays, overload relays, fuses, circuit breakers, motor starters, VFDs, soft starters, SPDs, insulation monitoring devices, ground fault protection, harmonic filters, and power quality analyzers. Proper coordination between these protection devices is crucial to ensure that they work together effectively to protect the motor and the electrical system. Regularly inspect and maintain motor protection devices to ensure their proper operation. This includes visually inspecting the devices for any signs of damage or deterioration, testing their functionality, and calibrating them as needed. Keep accurate records of all motor protection activities, including inspections, tests, maintenance, and repairs. These records provide a valuable history of the motor protection system and help track its performance over time. Stay up to date with the latest industry standards and best practices for motor protection. This includes attending training courses, reading technical publications, and participating in industry events. Understanding the latest advancements in motor protection technology can help improve the reliability and safety of electrical systems. Single phasing can cause significant damage to three-phase motors if left unaddressed. When one of the three phases is lost, the motor continues to operate on the remaining two phases but with reduced torque and increased current. This can lead to overheating, insulation breakdown, and ultimately motor failure. Phase loss protection is designed to quickly detect and respond to single phasing conditions, preventing motor damage and ensuring reliable operation. Choosing the right phase loss protection device depends on several factors, including the motor's horsepower, voltage, and application requirements. Consider the specific needs of the motor and the electrical system to select the most appropriate protection device. Installing and maintaining phase loss protection requires qualified personnel with expertise in electrical systems and motor protection. Ensure that the installation is performed according to the manufacturer's instructions and that the system is regularly inspected and maintained. When implementing phase loss protection, it is important to coordinate with other protection devices such as overload relays and circuit breakers to ensure that the motor is fully protected from various types of electrical faults. Proper coordination can prevent nuisance tripping and ensure that the motor is only disconnected when necessary. Phase loss protection can significantly reduce downtime and maintenance costs associated with motor failures. By preventing motor damage from single phasing, phase loss protection helps extend the motor's lifespan and reduce the need for costly repairs or replacements. Implementing phase loss protection improves the overall reliability and safety of electrical systems. By protecting motors from single phasing, phase loss protection helps prevent equipment damage, electrical hazards, and disruptions to critical processes. In some cases, single-phase conditions may be transient or intermittent, making it difficult to detect and respond to them effectively. Consider using advanced phase loss protection devices with adjustable time delays and sensitivity settings to minimize nuisance tripping and ensure reliable protection. Phase loss protection is not a one-size-fits-all solution. The specific requirements of each motor and electrical system should be considered when selecting and implementing phase loss protection. Work with qualified electrical engineers or technicians to assess the needs of the system and develop a customized protection strategy. Educate employees about the importance of phase loss protection and how to recognize the signs of single phasing. Training can help prevent accidental damage to motors and ensure that phase loss conditions are reported promptly. Consider using remote monitoring and control systems to track the status of phase loss protection devices and receive alerts when a phase loss condition is detected. Remote monitoring could help improve response times and minimize downtime. In addition to protecting motors from single phasing, consider implementing other power quality improvement measures such as voltage regulation, harmonic filtering, and surge suppression. These measures can improve the overall reliability and efficiency of electrical systems and protect motors and other sensitive equipment from various power quality disturbances. Regularly review and update phase loss protection strategies to ensure that they remain effective and aligned with changing operating conditions and system requirements. Continuous improvement is essential to maintaining a robust and reliable motor protection system. The cost of phase loss protection is typically a small fraction of the cost of repairing or replacing a damaged motor. Investing in phase loss protection is a cost-effective way to protect valuable equipment and prevent costly downtime. Phase loss protection is an essential component of a comprehensive motor protection strategy. By preventing motor damage from single phasing, phase loss protection helps improve the reliability, safety, and efficiency of electrical systems. The type of motor starter employed plays a crucial role in the protection and control of electric motors. Different types of motor starters offer varying levels of protection and control features, and the selection of the appropriate motor starter depends on the specific application requirements and motor characteristics. Firstly, across-the-line starters, also known as direct-on-line starters, are the simplest and most common type of motor starter. These starters apply the full line voltage directly to the motor terminals, resulting in high inrush current during starting. Across-the-line starters are suitable for small to medium-sized motors in applications where inrush current is not a major concern. Secondly, reduced voltage starters reduce the voltage applied to the motor during starting, limiting the inrush current and minimizing voltage dips in the electrical system. Reduced voltage starters are commonly used for larger motors in applications where high inrush current can cause problems. Thirdly, autotransformer starters use an autotransformer to reduce the voltage applied to the motor during starting. These starters provide smooth acceleration and adjustable starting torque. Autotransformer starters are suitable for applications where controlled starting and adjustable torque are required. Fourthly, resistor starters use resistors in series with the motor windings to reduce the voltage applied to the motor during starting. These starters are simple and cost-effective, but they can be less efficient than other types of reduced voltage starters. Fifthly, reactor starters use reactors, also known as inductors, in series with the motor windings to reduce the voltage applied to the motor during starting. These starters are similar to resistor starters but offer improved performance and efficiency. Sixthly, part winding starters connect only a portion of the motor windings to the power supply during starting. This reduces the inrush current and starting torque. Part winding starters are suitable for motors designed for part winding starting. 7th, Y delta starters connect the motor windings in a Y configuration during starting and then switch to a delta configuration once the motor reaches a certain speed. This reduces the starting current and provides smooth acceleration. Y delta starters are commonly used for medium to large size motors. 8. Variable frequency drives provide the most advanced motor control and protection capabilities. VFD can precisely control the motor's speed and torque, optimizing its performance and energy efficiency. VFD also provide built-in protection features, such as overcurrent, overvoltage, undervoltage, and phase loss protection. 9th, soft starters reduce the inrush current during motor starting, minimizing voltage dips and mechanical stress on the motor and connected equipment. Soft starters gradually increase the voltage applied to the motor, allowing it to start smoothly and without excessive current draw. 10th, solid-state starters use solid-state devices, such as thyristors, to control the voltage applied to the motor during starting. These starters offer precise control and smooth acceleration. Solid-state starters are commonly used for demanding applications where precise motor control is required. Selecting the appropriate motor starter depends on several factors, including the motor's horsepower, voltage, application requirements, and the characteristics of the electrical system. Consider the specific needs of the motor and the electrical system to select the most suitable motor starter. Motor starters should be installed and maintained by qualified personnel with expertise in electrical systems and motor control. Ensure that the installation is performed according to the manufacturer's instructions and that the system is regularly inspected and maintained. Proper coordination between the motor starter and other protection devices, such as overload relays and circuit breakers, is crucial to ensure that the motor is fully protected from various types of electrical faults. Good coordination can prevent nuisance tripping and ensure that the motor is only disconnected when necessary. Consider the environmental conditions in which the motor starter will be operating. Select a motor starter that is rated for the specific environmental conditions, such as temperature, humidity, and dust. Motor starters can be customized with various options and accessories to meet specific application requirements. These options may include pilot lights, push buttons, selector switches, and communication interfaces. Properly sized conductors and overcurrent protection devices are essential for ensuring the safe and reliable operation of motor starters. Refer to the National Electrical Code, NEC, and other applicable standards for guidance on selecting the appropriate conductor size and overcurrent protection. Regular inspections and maintenance are essential for ensuring the continued reliability and performance of motor starters. Inspections should include visual checks for damage or deterioration, as well as functional tests to verify proper operation. When troubleshooting motor starter problems, start by checking the power supply, control circuit, and motor connections. Use a multimeter to verify voltage and continuity. Consult the manufacturer's instructions and wiring diagrams for guidance on troubleshooting specific motor starter models. Proper grounding is essential for protecting personnel and equipment from electrical shock hazards. Ensure that the motor starter and motor are properly grounded in accordance with applicable electrical codes and standards. Motor starters should be clearly labeled with appropriate warnings and instructions. This helps prevent accidental operation and ensures that personnel are aware of the potential hazards. Employees should be trained on the proper operation and maintenance of motor starters. Training can help prevent accidental damage to equipment and ensure that motor starters are operated safely. Motor starters play a critical role in the protection and control of electric motors. By selecting the appropriate motor starter and implementing proper installation, maintenance, and operating procedures, users can ensure the safe, reliable, and efficient operation of the motor-driven equipment. Implementing a robust ground fault protection system is crucial for ensuring the safety of personnel and equipment in industrial and commercial facilities. Ground faults occur when electrical current leaks from energized conductors to ground, creating a dangerous shock hazard and potentially causing equipment damage or fire. Ground fault protection systems are designed to quickly detect and interrupt ground faults, minimizing the risk of electrical shock and preventing equipment damage. Ground fault protection is typically implemented using ground fault circuit interrupters, GFCI, and ground fault relays, also known as ground fault monitors. GFCIs are designed to protect personnel from electrical shock by quickly interrupting the circuit when a ground fault is detected. GFCIs are commonly used in residential, commercial, and industrial settings, particularly in areas where there is a risk of contact with water or moisture. Ground fault relays are designed to protect equipment from damage caused by ground faults. These relays continuously monitor the current flowing in the grounding conductor and trip the circuit breaker when a ground fault is detected. Ground fault relays are commonly used in industrial and commercial facilities to protect motors, transformers, and other electrical equipment. The National Electrical Code, NEC, requires ground fault protection for certain types of electrical equipment and in certain locations. The specific requirements for ground fault protection vary depending on the application and the voltage level. It is important to consult the NEC and other applicable standards to determine the specific ground fault protection requirements for a given installation. Ground fault protection systems should be tested regularly to ensure that they are functioning properly. GFCI should be tested monthly using the test button on the device. Ground fault relays should be tested annually using a ground fault test kit. Ground fault protection systems should be inspected regularly for any signs of damage or deterioration. Damaged or deteriorated components should be replaced immediately. Ground fault protection systems should be properly maintained to ensure their continued reliability. Maintenance should include cleaning, tightening connections, and lubricating moving parts. Employees should be trained on the proper operation and maintenance of ground fault protection systems. Training should include how to test GFCIs, how to inspect ground fault protection equipment, and how to respond to ground fault alarms. Ground fault protection systems should be clearly labeled with appropriate warnings and instructions. This helps prevent accidental operation and ensures that personnel are aware of the potential hazards. Ground fault protection is an essential component of a comprehensive electrical safety program. By implementing a robust ground fault protection system, facilities can significantly reduce the risk of electrical shock and prevent costly equipment damage. Ground fault protection is not a one-size-fits-all solution. The specific requirements of each installation should be considered when selecting and implementing ground fault protection. Work with qualified electrical engineers or technicians to assess the needs of the facility and develop a customized ground fault protection strategy. Ground fault protection systems should be coordinated with other protection devices, such as overcurrent protection and surge protection, to ensure that the electrical system is fully protected from various types of electrical faults and abnormal operating conditions. Proper coordination can prevent nuisance tripping and ensure that the electrical system is only disconnected when necessary. Consider using ground fault protection systems with advanced features such as adjustable sensitivity settings, remote monitoring, and data logging. These features can help improve the performance and reliability of the ground fault protection system and provide valuable insights into the health of the electrical system. Implementing a robust ground fault protection system is an investment in safety and reliability. By protecting personnel and equipment from ground faults, facilities can reduce the risk of accidents, prevent costly downtime, and improve overall productivity. Ground fault protection is a critical component of a comprehensive electrical safety program. By implementing a robust ground fault protection system, facilities can significantly reduce the risk of electrical shock and prevent costly equipment damage.